Hello friends, welcome. Friends, I get a lot of question about BSNL's poor quality network. One of the question that was a viewer had written 3 days ago is right in front of your screen. You can pause the video and have a look. In net, what he is trying to say that BSNL has got a very poor indoor penetration. Saying that when I go beyond a thin wall, the network is totally destroyed. I don't get 4G, 3G, 2G, nothing. He gets nothing, right? And he is literally frustrated. Now, how do I answer this question? It becomes a little difficult for me to answer such a question which involves a lot of technical explanation. But I will make an attempt to try to answer this question, though there will be technical points which I'm going to make, but I'm not going to deep dive into those equations. Because if I deep dive into those equations, then viewers who are listening to me, who do not have an understanding of technicalities, they will find this video not very useful. That's why I will keep the video up, elevated so that anybody, any layman can understand. Now, friends, in order for you to understand what is going wrong with BSNL, it is important to look at their BSNL spectrum pyramid. So this is the BSNL spectrum pyramid right in front of you, right? So if you see here, let me just pause the video here. This is a animation which I have created. So if you see here, this BSNL network has these many spectrum. We've got 3500 megahertz spectrum, 70 megahertz. Then we have got 2500 megahertz spectrum, 20 megahertz. Then we have got the 2100 megahertz spectrum broken into two pieces, 5 megahertz each, one doing 4G, another doing 3G. And then we have the 700 megahertz 4G, 10 megahertz, which is 4G, and the 900 megahertz GSM 6.2 for 2G. And all these phones are connected to the respective network. You can pause the video and have a look at this, right? So just memorize this information. So point to be noted here is that 700 megahertz has got a larger reach and a greater bandwidth. Similarly, GSM also has got a larger reach, but the bandwidth is low. And the 3G and the 4G network in 2100 megahertz has got very small bandwidth and their coverage is also poor. Okay. Now, let's go to the Excel sheet, which I'm going to use to answer this question. Now, what is this Excel sheet? You should not get overwhelmed by this Excel sheet because whenever I try to answer question, I get into calculations. Without getting into calculation makes no sense, right? But I need to make you understand these parameters and this working block which is down below, without which you will not be able to appreciate what I'm saying, right? Now, you will find that in my Excel sheet, there are two different tabs. One is BTS to UE. BTS to UE means what? BTS to handset, right? The BTS is transmitting, base station is transmitting, handset is receiving. And then handset to BTS, handset is transmitting and base station is receiving. There are two different models I have created in my Excel sheet. Okay. Now, what I am having here, which user can change, is the distance, the frequency. Let me just plug in 700 here because I can plug in 700 here, right? Then I can change the bandwidth. Let me plug in 10 megahertz here, right? You just ignore this line. BTS transmit power, people will understand very easily. 46 dBm for a typical 700 megahertz base station, which is relatively high. It can be lower also, 43 dBm, right? Now, dBm to watt conversion, etc., I'm not going to get into. Otherwise, the video will go into a completely different direction. Assume that dBm is a power unit, right? Why dBm? Because it becomes very easy to add, right? Otherwise, if you had used watts and etc., it becomes very difficult because the power levels go so low that only way to measure those power levels is using dBm. It makes the logarithm curve linear. That's all. Okay. Then the transmit antenna gain is 17 dBm. Now, what is antenna gain? Antenna gain, as I've been telling you in other video, it is just the elliptical shape of the RFA, which is the power gets concentrated not in a circular spherical wave, but in an elliptical wave so that it gets focused in the forward direction so you can travel more. That is what called 17 dB here, right? So that amount of focus of the power is being measured using this 17 dBm number. Now, UE gain, UE means handset antenna gain, is 0 means it has to be omnidirectional. It can't have a directed antenna. If it had a directed antenna, then you will not know which direction the signal is coming. You have to sit and point the handset towards the base station to receive the signal. You forget about this. This is thermal noise. This is a value which you can very easily calculate. This is called Boltzmann noise, KT. Again, I don't want to get into it. I lose the view. This is noise figure. Let me explain this noise thing very clearly. What type of noise which you encounter into the system? Let's say if you have a BTS here and a handset here. Just make an assumption here. So there is a path which you have to traverse in order to reach the handset. Now, when you are traversing this path, you have to encounter an atmospheric noise, which will always remain in the system, which is driven by this KT. This is called thermal noise, dBm per hertz. Why dBm per hertz? Means, let's say if you have a bandwidth here, that bandwidth, every hertz of the bandwidth will have this value, minus 174 dBm per hertz. Now, if you have a 10 megahertz of bandwidth, you have to multiply this by 10 in order to calculate the total thermal noise in that bandwidth. You understand now? This is called one noise. Another noise is, let's say if there is a receiver. Now, receiver, when it gets the signal in, let's say signal is entering this receiver, there will be electronics here within the receiver. That electronic adds additional noise on top of this thermal noise, and therefore it becomes noisier. And that noise is called the noise figure, means how much additional noise the receiver has had. You can read here, I have written, right? And what is this bits per hertz cap per layer? This is called 3.32. Again, don't get lost, right? Please be with me. It's very important. This is the spectral efficiency for a particular technology and for a particular coding scheme. Let's say if I use a different coding scheme, I can get a better efficiency. For example, if I use LTE 256 QAM, I get a bits per efficiency of 5.5. Now, if I use another technology called NR 1024 QAM, I'll still get a better bits per hertz efficiency. That's all, nothing else. The coverage does not change, only the throughput becomes better if you use a better, coding, scheme. I will use LT 64 QAM because if you go into the higher coding, the complexity increases, the device price will increase. Now, this is important. This is called SINR. Now, what is SINR? SINR includes not only the thermal noise and the receiver noise, but also the interference noise. Now, what is interference? Interference is other users who are using the same RF wave which you are locked in. Let's say if you have an elliptical RF wave here like this, then there are so many other users who are going to use the same RF wave, which will lead to interference. Means if you are alone, then there will be no interference noise. But that is not a practical situation. There will be multiple such users all the time using the same block of RF wave which you are locked into, right? So that's why this interference noise depends upon which model that I am using. Means model time means whether urban outdoor, urban indoor, urban rural outdoor and rural indoor. So this is that. Okay. So this value, which is called SINR, because I told you that there is interference also. So signal to noise ratio, which includes all types of noise. The thermal noise, the noise figure, which is the receiver noise, as well as the interference noise. So this is not just signal to noise. This includes interference as well. And therefore, without interference, if whatever calculation you do is not going to make sense. And this number 9.54 is emanating out of an equation which I don't want to explain to you here. Just be with me. If I change the bit rate here, bits per hertz, this number is going to change. You see 5.5, this number becomes different. 7.25, this number becomes different. Why this number becomes different and what is the utility of this number? This number tells you that you require a minimum, this number, signal to noise ratio including interference of 9.54 in order to utilize this full bit per hertz efficiency. Means whatever is the throughput that you are getting in the bandwidth 10 megahertz will remain constant, irrespective of the fact that your SINR goes above this value. Means this is the minimum that you need. You understand now? If it goes below, then this efficiency will go down, your throughput is going to go down. You understand now? That is the reason why this is capped at 9.54, and if you're going to use a different coding technology, the value has to go higher in order to decode that. That is the reason why, if you are using a lower QAM, it will be able to decode the signal better, because you need a lower signal to noise including interference ratio to decode that signal and get that bit per hertz efficiency. Okay, so this is, you have understood. Another thing which is pretty important, which I have not explained yet, called path loss exponent. What is path loss exponent? Normally, when you are transmitting a signal from a BTS, this is going to be spherical in nature, right? So how do you calculate power density? Power density is the power that has been emanating out of this point where the antenna port, and the radius of this, which will give you the area of the sphere. So power density will be the power divided by the area of the sphere, which is 4 pi r square. Now, this happens only in case of free space, 4 pi r square. Now, if it is not free space, then it is not 4 pi r square, it is something else. 4 pi r to the power 3.25, 4 pi r to the power 4, 4 pi r to the power 2.5, 4 pi r to the power 3. This is called the path loss exponent. So if it was free space, then I have to simply replace this 3.25 by 2, right? Got it? So this is this particular. What is this body penetration fade? This is what the body penetration and indoor thing, which the viewer asked. Let's say if you are in an urban indoor and there are very thick walls, and you are holding the mobile phone in your ear like this, there will be a loss because of this, your way you are holding the mobile phone, and all those deep concrete blocks are going to create this loss. Therefore, if you see urban indoor, I have put a value of 23 dB. Whereas urban outdoor, it is 8. It is almost similar for rural outdoor, and rural indoor, I have reduced it to 17 dB, right? Noise, I have already explained to you. Interference noise, which I have already added, because if it is heavily loaded, in case of urban, it will be heavily loaded. Therefore, I have given 12. In indoor, it is 9 because there will be some kind of shielding because of that. And this. Layers is how many paths are there, MIMO. If you have got 2 antennas, transmitting antenna, 2 layers. If you have 1 layer, right? Efficiency, you just forget about it. This is the free space path loss without including the transmit antenna and the transmit antenna power and the transmit antenna gain. So if it is base station to handset, then free space path loss is this number for these values which I have already explained to you. Okay, these are. And then what is the power at the receiver end? What you have to do? The transmit power, the antenna gain, and the free space path loss has to be subtracted. This is the equation. Where is that equation I had? Anyway, forget about the equation. As soon as I show you equation, people will lose me, right? So this is what? The receiver power at the receiver end. And then if you add the noise floor, because this is at the receiver antenna port, what you have to do? You have to add this 7 dB, right? Which is going to be the noise floor. Actually, not add, you have to subtract 7 dBm in order to get this number. Not 7 dBm, you have to basically do the full noise thing, right? Noise floor over bandwidth. The whole thing you have to calculate, which I will show you one chart how to calculate noise. Just pause the video, you will be able to understand it. Otherwise you'll get confused. So let's do the following. Path loss calculation is here, right? So anybody who is interested in knowing how path loss is calculated can pause the video and look at this. Okay, right? And then noise interference is here. Pause the video and look at this. It is quite complex here, but I don't want to go through each and every point. Otherwise, viewers are going to lose it. But some viewers may be interested, and therefore I am giving you this. Pause the video and have a look at it, right? Now, let's go to the point which I was basically mentioning. Just a minute. Just hold on for a minute. I'll just put it here where it was, right here. So I'm back here. Now, what I'm getting, now I am getting the SNIR. All this effort that I did from the beginning till the end is to come out with this value, SNI, which you will get here. Where you will get? You will get here. Where is that? Calculation here. You see? This is the final calculation here. Okay. So this is where I have the calculation of SM. Now, data throughput is the calculation. How do you calculate data throughput? The data throughput is a little complex calculation. Just be with me, otherwise you will lose it, right? Now let's play with the numbers. Then you will understand what you go. You just focus on this column and this column. That's all. That will answer your question. Now the viewer question was what? Let's go back to the viewer question. The viewer had asked the following question. Where is it? He's saying that indoor penetration of 2100 megahertz band is pretty poor. And I'm not, and BSNL all, even 4G, 3G, everything is very poor. So let me do the following. Let's do first the BTS to handset, and I'm replace it with 2100 megahertz band, and I'll make the bandwidth 5 megahertz. And then you will see that the distance I'm going to basically reduce it to, let's say 5. Okay. Now you will see that in case of urban indoor, with all these parameters, you will be able to get a throughput of 7.1 in 5 using these values. 2100 megahertz, bandwidth of 5 megahertz, and all these numbers are constant. Rural indoor, you should get 13.61. Why you are not getting it? Maybe it is because the distance may be higher, or these values are going to be higher. If the distance, if I increase to let's say 10 kilometers, you see what is happening to urban indoors. So this is the one of the reason why you are getting, or you have to play with these numbers. Rest of the numbers do not change much, but play with these numbers, right? So this is one. So this is about BTS to handset. Now let's go the reverse direction and see what happens, because the reverse direction, the equation completely changes. So what I have done here, distance I have taken 2.5, I'll change it. Let's make it 5. Okay, 2100 megahertz, 5 megahertz. Look at the SINR. You need how much? 9.54. Look at the numbers and look at what you are getting in rural indoor and rural outdoor as far as throughput. It is hardly anything in 5 kilometers. So if you are in 2.5, let's say, distance, you may get a better speed upload, because upload is always going to be challenged because the transmit gain of the antenna is going to be 0. Right? And the transmit power of the antenna is going to be 23 dBm because of EMF issue, which the handset is going to transmit. In case of BTS, it was 46 dBm. In case of handset, it is 23 dBm. That is why your numbers will fall significantly. So the radius of coverage that you get is not determined by BTS to UE. It is determined, BTS to handset, it is determined by handset to base station because of these values and because of what the SNIR you are getting, SINR you are getting, which includes interference. And if your body penetration, fading, etc. is much higher, right, because the network is not properly configured, you will get nothing. Even in 2.5 kilometers, you are getting 1.101 Mbps. In urban indoor, rural, you are getting a fair good number. But if this I change, let's say from 17 dB, I make it 25. Imagine how much you are getting here, 1.21. If I make this, let's say 27, you are getting 0.79, right? I make it to 17. So this may be one of the reasons. Or the other reason could be the antenna gain of the BTS may not be properly tuned. It may not be 17 dB. It may be wacky. The design may be wacky. It may be, let's say, 5 dB gain. Look at this, what happens in 2.5. See? Right? Similarly, if I put here 5 dB gain and your antenna is not properly tuned, you see what happens here. So that is the point here, friends. Your network is not properly tuned. Your network is having the antenna gain may not have been properly configured. Your indoor penetration losses may be very, very high. You may be having multiple walls, right? Your BTS may be far, far from the point where you are. And your tilting may not be proper. So these are the things which actually kind of adds up and creates this kind of problem that you are seeing as far as data throughput is concerned. So this is just an indicative video, friends, to give you a feel as to why you are getting this kind of problem, friend. Right? There are many things which needs to be managed in order for you to get a better signal and better throughput. If there is some kind of suboptimality in the numbers that I've showed you here, especially the transmit power, the transmit antenna gain, the receive power, whatever noise, and your design of your handset, design of the BTS, if it is adding too much noise, right? All these things will add, and the penetration losses are also going to add significantly towards the path loss, and the data throughput is going to go down and get a very poor quality signal. So that's all, friend. This was a very complicated thing to discuss and explain, because there are many things which I have left out, and I'm just showing you this big calculations which I have done for viewers to have a look at it, right? You can pause the video, and if anybody is interested, you can understand or ask another question, and I'll try to clarify each of the individual points which I mentioned in this video separately. So thanks for listening till the end. I'll come back with a new video on a new topic next time. Thank you very much, friends.